Most of the universe is nothing. Not thinly populated, not sparsely scattered. Organised, structured, ancient nothing. Spheres of near total emptiness stretching hundreds of millions of light years in every direction, so thoroughly evacuated that light passes through them for millions of years without touching a single thing. We have catalogued over 8,000 of them. We live inside one. And here is the thought that has been quietly circulating at the edges of serious scientific discussion for years. Absence of light is not the same as absence of life. We detect civilizations by their glow. We map the universe by what shines. But what if the oldest, most sophisticated things in existence stopped shining on purpose, and what we are calling empty space is actually the most occupied real estate in the cosmos? Tonight we follow that possibility to its conclusion. If you are new here, welcome. Subscribe, get comfortable, and stay until the end. Because by the time this is over, the emptiness out there is going to feel a great deal more crowded than it does right now. Now, let's get into it. Part 1. The Lie of a Universe Full of Stars. Here is something nobody told you in school. The universe is not full, not even close. When most people picture space, they picture what they have seen in movies and textbooks. A field of stars stretching wall to wall, galaxies glittering like scattered salt on black velvet, matter everywhere you look. It is one of the most persistent illusions in human history. The idea that the universe is a kind of cosmic ocean, dense and continuous, filled in every direction with burning things and spinning things and ancient things. We grew up with that picture. Posters on classroom walls, NASA photography. The Hubble Deep Field image showing what looked like thousands of galaxies crammed into a patch of sky, the size of a grain of sand held at arm's length. It all gave us the same subconscious message. Space is full. It is not. And the moment you truly understand how wrong that picture is, something shifts in how you see everything. Here is the real model. Imagine a foam. Not the tight, almost solid foam in a sofa cushion, but the kind of foam you see when someone shakes a bottle of dish soap. Enormous bubbles separated by the thinnest possible membranes, with most of the volume being the air inside the bubbles themselves. Now scale that foam up to the size of the observable universe. The thin, fragile membranes where the bubbles touch, that is where the galaxies live. That is where the stars are. That is where you are. And the bubbles themselves, the interior of each one, the vast, overwhelming majority of the total volume, contain almost nothing. Not low density, not sparse, almost nothing. This is what cosmologists call the cosmic web, and it rewrites everything you thought you knew about where we live. Galaxies are not sprinkled evenly through space. They are not the dominant feature of the universe. They are edge phenomena. They exist at the margins, along the boundaries between enormous structures of emptiness, clinging to the surfaces of something so much larger than themselves that calling them the main feature of the universe would be like saying the crust of bread is the main feature of a loaf, while ignoring the fact that most of the loaf is air. The galaxies are real. The stars are real. But they are not the story. They are the decoration on the edge of a structure built almost entirely from absence. Astronomers have a name for the interiors of these enormous foam bubbles. They call them voids. And when you start learning what voids actually are, their size, their age, their dominance over everything else, the word feels almost insultingly small. A typical void is somewhere between 10 and 100 megaparsecs across. 1 megaparsec is about 3.26 million light-years. So a small void, a modest, unremarkable void that nobody writes papers about, is roughly 32 million light-years from one side to the other. To cross it at the speed of light, which is the fastest anything in the universe can travel, 300,000 kilometers per second, would take 32 million years. You could cross it 200,000 times in the time since the first dinosaurs walked the Earth. And those are the small ones. Supervoids, the extreme cases, the outliers that make cosmologists stop and double-check their data, can stretch across hundreds of millions of light-years. Some have been measured at over 1 billion light years in diameter. 1 billion light years. If you tried to drive across one of those at highway speed, and the highway somehow stretched through intergalactic space, you would have started your trip approximately 14 times before the universe itself existed. The galaxies we see, the ones in all the photographs, they do not live inside these structures. They crowd at the edges, and that means the overwhelming majority of the observable universe, by volume, by sheer geometric domination, is not filled with matter. It is not filled with light. It is structured absence, organized emptiness, a darkness so thorough and so ancient that it has its own physics, its own behavior, its own role in the architecture of everything. This changes the story. We're not inside a universe that is full of things. We're inside a universe that is mostly hollow, with matter existing only along the thinnest of membranes stretched across a framework of nothing. And the deeper you look into what that nothing actually is, where it came from, what it does, what it might contain, the stranger this universe becomes. Because here is the question nobody asks when they look at a void on a cosmological map. How do we know it is actually empty? Part 2. The hidden architecture of reality. The cosmic web is not a metaphor. It is a real physical structure, and the fact that it took humanity most of its scientific history to even notice it is one of the more humbling episodes in the story of cosmology. For most of the 20th century, the default assumption among cosmologists was that the universe was, at large enough scales, essentially uniform, smooth, homogeneous. Yes, galaxies clustered together here and there. Yes, there were local overdensities and gravitational groupings, but zoom out far enough and everything would average out. Matter spread evenly in all directions. No large-scale patterns, no architecture, just a continuous isotropic distribution of galaxies fading into the distance in every direction like fog. That assumption turned out to be one of the most spectacularly wrong ideas in the history of science. The first serious cracks appeared in the 1970s, when astronomers began building something called redshift maps. The concept is elegant in its simplicity. Every galaxy is moving, and as it moves away from us, the light it emits gets stretched to longer, redder wavelengths. The faster the recession, the greater the redshift. And since the universe is expanding and distance correlates with recession speed, redshift tells you how far away a galaxy is. So astronomers began systematically measuring the redshifts of thousands, then tens of thousands, then hundreds of thousands of galaxies, and plotting them in 3 dimensions. They were drawing a map. A real map of the universe as it actually exists in space. What they found was so unexpected that many researchers initially assumed there was an error in their data. The galaxies did not distribute evenly. They did not smooth out at large scales. Instead, they formed long, thread-like structures stretching across hundreds of millions of light years, filaments of matter connecting galaxy clusters the way spider silk connects anchor points. Between these filaments, occupying the spaces the filaments did not reach, were enormous voids, not sparse regions, not thin areas, genuine emptiness, volumes of space containing almost no galaxies at all, volumes sometimes larger than anything the astronomers had expected to find in a universe supposedly governed by uniform randomness. The first major void to be mapped with real precision was discovered in 1978 and confirmed over the following years in a region of sky near the constellation Boötes. The researchers stared at their data expecting to find the usual distribution of background galaxies. Instead, they found a hole, a sphere of space roughly 250 million light-years in diameter, containing, in the words of one of the astronomers involved, far fewer galaxies than anyone had expected to find there. Later surveys would refine that count. It was not just far fewer, it was almost none. But we will come back to Boötes, because first you need to understand the full architecture it sits inside. The cosmic web has 3 primary components. Filaments are the visible skeleton, long, roughly cylindrical structures of matter where galaxy clusters collect, and where the density of the universe is highest. Superclusters and galaxy clusters form at the intersections of filaments, at the nodes where multiple threads of matter converge, and gravity has had the most time and material to build the most massive structures in the universe. And voids are everything else. Every region that is not a filament, not a cluster, not a wall, which is the name for the flat, sheet-like structures where filaments meet from multiple directions. Every other part of the universe is a void. And here is the number that should reset your understanding of space. Voids occupy somewhere between 60 and 80% of the total volume of the observable universe. Some estimates push that figure higher. The point is not the exact percentage. The point is that the feature that dominates the universe, the thing that takes up the most space by an enormous margin, is the thing we spent most of our history ignoring. The thing we still call by a word that means nothing. Gravity shaped this structure. Dark energy is stretching it. Time built it up over billions of years from seeds so small they were quantum fluctuations in the first fractions of a second after the Big Bang. And the result is a universe that looks, at the larger scales, almost exactly like soap foam, matter collecting at boundaries, emptiness filling the interior, with the pattern repeating at scale after scale in something close to a fractal geometry. This is the universe, not a field of stars, not a distribution of galaxies, a foam-like lattice of matter wrapped around structures of emptiness that dwarf everything the matter has ever managed to build. And understanding that architecture is what makes the anomalies so disturbing, because the anomalies are the places where even that model breaks down. Part 3. The scale that breaks intuition. There is a specific moment in learning about cosmic voids where your brain's sense of scale simply stops functioning. It happens somewhere around the point where you try to actually visualize how large these structures are, and your mental machinery, which evolved to track predators and remember where berries grew, gives up completely. Let us try anyway. Let us start with something already almost incomprehensibly large and build from there. The Milky Way galaxy, your home galaxy, the one containing our sun, our solar system, and somewhere between 100 billion and 400 billion other stars, is approximately 100,000 light-years across. 100,000 years of light-speed travel end to end. That number is already outside normal human intuition. If you scaled the Milky Way down to the size of a dinner plate, the nearest large galaxy, Andromeda, would be about 6 feet away, and everything else would be much, much further. A typical cosmic void is roughly 30 million light-years across on the small end. Scale that to the dinner plate Milky Way, and the void is not 6 feet away. It is the size of a house, a large house, and that is a small void. A super void at 300 million light-years across, on that same scale, would be the size of a city block. 1 billion light-years across. You're now comparing a dinner plate to a structure roughly the size of the island of Manhattan, and the void contains almost nothing. Think about what that means in terms of matter distribution. A galaxy cluster, one of the densest, most massive structures in the universe, might contain hundreds of individual galaxies within a region perhaps 10 to 30 million light-years across. That cluster, that concentration of hundreds of galaxies, could fit inside a single small void with room to spare, and it would be dwarfed by the emptiness surrounding it. The void does not care about the cluster. The void is 400 times larger in diameter and billions of times larger in volume, and the cluster sits in it the way a single raisin sits in a swimming pool. Now consider this. If you wanted to travel from one side of a large supervoid to the other, and you were travelling at the speed of light, and you cannot, nothing with mass can, the journey would take hundreds of millions of years. The dinosaurs appeared on Earth about 230 million years ago. You could board a light-speed vessel on one side of a supervoid, travel for the entire age of the dinosaurs, and still not be halfway across. And there are more than 8,000 catalogued voids in the observable universe. 8,000. That is not a quirk. That is the dominant architectural feature of everything we can see. Each one is a sphere of near nothing, each one representing a volume of space that overwhelms by sheer size everything matter has ever built. The galaxies, the stars, the black holes, the nebulae, all of it, everything we have ever photographed or measured or named, exists in the thin membrane of structure between these 8,000 holes. This is not a universe full of things. This is a universe made mostly of organised holes, with a thin lattice of matter clinging to their surfaces. And before we go any further, let us hold on to something important. We know what the conventional explanation for these voids is. We understand the physics, at least in outline. Gravity drained matter away. Expansion stretched the gaps. Time and cosmological mechanics built the foam. We have models. We have simulations that produce foam-like structures that match what we observe. For most voids, the conventional story is probably correct. But for some of them, the conventional story starts to strain. For some of them, the numbers come back just a little too extreme, and there is one in particular, one specific void that has had a name since 1981, that cosmologists keep coming back to, not because it proves anything, but because it refuses to become comfortable. Part 4. The first psychological collapse. Take a moment. Step back from the data and the distances and the scale comparisons. Just sit with what you've just learned, because there is a psychological dimension to this that the numbers alone do not capture. You grew up in a universe that felt full, populated, active. The night sky, even in a city where light pollution washes out most of the stars, gives the impression of a sky that has things in it. Go somewhere dark, a desert, a mountaintop, somewhere without electric light for miles in any direction, and look up. The Milky Way stretches overhead like a river of light. The feeling it gives is abundance, presence, fullness. The sense that you are standing beneath something enormous and populated, something that extends outward in all directions and fills space the way water fills a glass. That feeling is a lie, a beautiful, ancient, deeply understandable lie, but a lie. The light you see from any dark location represents a vanishingly small fraction of the universe's volume. The stars that make up the Milky Way are all crammed into a tiny strand of one filament among millions. The galaxy clusters visible to the naked eye are nodes in a web whose dominant structure is the space between the web threads. The sky feels full because you are surrounded by the rare thing, not the common thing. You live on the edge of a void. You look out from a membrane of matter into darkness that extends, in some directions, for hundreds of millions of light years without interruption. Emptiness is not the exception in this universe. Emptiness is the rule. Matter is the exception. Galaxies are the exception. Stars are the exception. You are the exception. Everything you have ever known, every civilization that has ever existed, every book written and every war fought and every signal ever broadcast into space, all of it has happened on a thin film of structure, stretched across a framework of near-nothingness. There is something specific about this realization that feels different from other scale-shock moments in cosmology. Learning that the Sun is 1,000,000 times larger than Earth is shocking, but it does not change your relationship to space. Learning that the nearest star is 4 light years away is humbling, but it leaves intact the idea that space is at least trying to be populated. This is different. This is the realization that space does not even try. Space is, by default, by dominant tendency, by the nature of how the universe organizes itself, empty. We are not surrounded by a cosmos full of structure that sometimes leaves gaps. We are surrounded by a cosmos full of emptiness that sometimes, at the edges, allows matter to accumulate. Cosmic loneliness is not an emotional state. It is a structural condition. And now, sitting with that, ask yourself, where did this enormous emptiness come from? How does a universe start from a single point, from a state of near infinite density, and produce over 14 billion years something that is more than 60% organized nothing? How does the universe build its own absence? That is the next question, and the answer reaches back to before the first second of time. Part 5. The birth of emptiness. The emptiness did not arrive late. It was not a product of the universe thinning out over time, of matter spreading away from a centre and leaving gaps behind. The voids we see today, those multi-hundred million light-year spheres of near nothing, trace their origins back to the first fraction of a second after the Big Bang. To a moment so early in the history of the universe that describing it in human terms requires numbers so small they are effectively meaningless to anything but mathematics. In the beginning, and in cosmology, the beginning means the first 10 to the negative 32 seconds. A decimal point followed by 31 zeros and then a 1, the universe was not smooth. It was not perfectly uniform. It could not be. Quantum mechanics does not allow for perfect uniformity. At the quantum scale, energy and density fluctuate constantly, not because something is disturbing them, but because fluctuation is a fundamental property of reality at small scales. These fluctuations are not errors or imperfections. They are the normal, unavoidable, baked-in behaviour of quantum fields. Under normal circumstances, at human scales, quantum fluctuations average out and disappear. You never notice them. But in the first instance of the universe, something happened that prevented them from averaging out. Something took those tiny sub-microscopic variations in density and stretched them across cosmic scales. That something is called inflation. Inflation is the name for a proposed period of extraordinarily rapid expansion in the very earliest universe, during which the fabric of space itself expanded at a rate so far beyond the speed of light that the observable universe went from smaller than a proton to roughly the size of a grapefruit in a time period that makes a femtosecond look leisurely. The exact mechanism is still debated. The energy source driving inflation is still unknown. But the observational evidence for something like inflation having occurred is strong, because inflation makes a specific prediction. It takes quantum-scale density fluctuations and stamps them across the early universe at cosmological scales. Those density fluctuations became the seeds of everything. Every region that emerged from inflation slightly denser than average had a little more gravitational pull. Over hundreds of millions of years, that slightly higher gravity attracted nearby matter, pulling it in, growing denser still, forming the first clouds of gas, then the first stars, then the first galaxies, then the first clusters. And every region that emerged slightly less dense than average had slightly less gravitational pull. Matter around it was pulled away toward the denser regions. Those under dense regions became emptier. Over billions of years, much emptier. Over the age of the universe, they became voids. This means the Bhuta's void, that region of space 250 million light-years across containing almost no galaxies, has an origin that predates the first stars by hundreds of millions of years. It was a statistical shadow, a region of space that happened, by pure quantum chance, to emerge from inflation with slightly below average density. That initial underdensity was not dramatic. It was not a hole. It was a whisper, a tiny variation in energy density across a region smaller than an atom. Inflation stretched that whisper to cosmic scales. Gravity spent 14 billion years amplifying it, and the result is a sphere of organised absence larger than your imagination can comfortably hold. The seeds of the universe's emptiness were planted before the first second of its existence. They were quantum accidents, frozen in place by the most violent expansion event in cosmic history, and then slowly, patiently, inexorably grown by gravity into the dominant structural feature of the observable universe. You're looking at 14 billion years of elaboration on a quantum fluctuation. That is what a void is. Which raises a question worth sitting with. If most voids trace to random quantum fluctuations amplified by inflation, what happens when you find one that seems too large, too empty, too structured for that explanation to feel comfortable? Part 6. Gravity's Great Sorting Machine. Gravity is a patient architect. It does not hurry. It does not need to. It has billions of years, and it uses every one of them. After inflation seeded the universe with those tiny density variations, gravity took over. The process that followed was not dramatic in human terms. No explosions, no sudden reorganizations, no moments of visible upheaval. It was slow, continuous, and utterly relentless. Matter flowed. Over millions of years, then hundreds of millions of years, matter moved from under-dense regions toward over-dense ones, not all at once, not fast enough to see in any human lifetime, but persistently, inevitably, following the gradient of gravitational attraction, the way water follows the gradient of a slope. Picture the universe as an enormous three-dimensional landscape of subtle hills and valleys, not physical terrain, but variations in density. The hills are regions of higher than average matter concentration. The valleys are lower than average regions, and matter, under the influence of gravity, behaves like water on that landscape. It flows downhill. It collects in the valleys. Except in this case, the geography is gravitational, not physical, which means the valleys that attract matter are the dense regions, and the hills that lose matter are the underdense ones. This inversion of intuition is important. In a gravitational landscape, you flow toward the heavy places. The denser a region, the more strongly it pulls surrounding matter toward itself. The less dense a region, the more its own matter gets pulled away. So the initially overdense seeds that inflation left behind got denser and denser over time, pulling matter from neighbouring regions, growing into filaments and clusters and walls. And the initially underdense seeds got emptier and emptier over time, bleeding matter out toward the neighbouring overdensities, gradually evacuating until they became what we now call voids. This is gravity behaving as a sorting machine. A slow, cosmic sorting machine that takes the nearly smooth universe left after inflation and spends billions of years amplifying every difference, separating matter from non-matter, building structure in some places by dismantling it in others. The cosmic web, all those filaments and clusters we discussed earlier, is not something that was placed in the universe. It grew from the universe's own substance through the operation of gravity over time. The matter was always there. Gravity just sorted it. And here is what makes voids the inevitable product of this process. The sorting machine never stops. It is running right now. At this moment, matter is draining out of underdense regions into the surrounding filaments and clusters. Voids that exist today are larger and emptier than they were a billion years ago. They will be even larger and emptier a billion years from now. The universe is not a static structure that gravity built and then left alone. It is an ongoing process, and the process is always in the direction of more extreme structure, denser clusters, emptier voids, thinner filaments stretched across larger gaps. There is a metaphor that captures this well. Imagine watching a river system grow from a flat, slightly uneven plain after a rainstorm. The water does not spread evenly. It finds the lowest points and channels there. Channels cut by early flow carry more water, which cuts them deeper, which carries more water still. The high ground becomes drier. The channels become rivers. The rivers carry almost all the water, and the high ground between them carries almost none. Run that process for long enough and the landscape develops into a network of rivers and dry plateaus, exactly analogous to the cosmic web of filaments and voids. Gravity is the rain, time is the time scale, and the voids are the dry plateaus left behind when all the water, all the matter, found somewhere else to flow. But here is what that means for the extreme cases. For a void to be as empty as Bhuta's void appears to be, the gravitational drainage must have been extraordinarily efficient. The initial underdensity must have been deeper, or the surrounding overdensities must have pulled harder, or both. The sorting machine must have worked on this particular region with unusual thoroughness. That is possible within the standard model. That is allowed by the physics. But when you actually run the numbers, when you ask whether the initial quantum fluctuation could plausibly have been deep enough, and whether 14 billion years of gravitational drainage is enough time to achieve what Bhuta shows us, the answer becomes, to put it diplomatically, less than fully comfortable. Part 7. Why voids don't stay stable. One of the important things to understand about cosmic voids is that they are not passive. They are not just empty regions sitting quietly while the universe does things around them. Voids are active participants in the large-scale dynamics of the universe, and they have a behaviour that, once you understand it, makes the existence of extreme supervoids feel both more understandable and, in some ways, more troubling. The key insight is this: voids grow, not the way stars grow or galaxies grow by accreting material. They grow the opposite way. Voids grow by losing material, by becoming more empty over time, not less. Here is the mechanism. Inside a void, the matter density is below the cosmic average. Below average density means below average gravitational attraction. The gravitational pull generated from inside the void is weaker than the pull generated by the filaments and clusters surrounding it. So matter on the edges of the void, matter that is technically part of the void's boundary, feels a net gravitational pull toward the outside, toward the filaments, rather than toward the interior. It drains. And as it drains, the void's interior becomes slightly less massive, which weakens its internal gravity further, which makes the drainage slightly more efficient, which leads to more matter draining, which weakens the gravity further still. This is a self-reinforcing cycle. Emptiness amplifies itself. The more matter a void loses, the more efficiently it loses matter. The process is not fast by human standards. We're still talking about cosmological timescales of hundreds of millions of years per significant change, but it is unidirectional and unstoppable. A void that exists today was less empty yesterday and will be more empty tomorrow, and the rate at which it becomes more empty is itself increasing over time. Now layer onto this the effect of dark energy. Dark energy is the name cosmologists give to whatever is causing the universe's expansion to accelerate. We do not know what dark energy is. We know it exists because we can measure its effects. The universe is not just expanding, but expanding faster and faster over time, and something has to be causing that. Dark energy is estimated to make up roughly 68% of the total energy content of the universe, making it the single most dominant component of the cosmos, and we have essentially no idea what it fundamentally is. But its effect on voids is significant. As dark energy accelerates expansion, the distances between filaments grow, the web stretches, and as it stretches, the voids between the filaments grow with it. They are expanding not just by draining matter inward to filaments, but also by the literal stretching of the space they occupy. The voids are growing in two ways simultaneously, by internal evacuation and by external expansion, and both processes reinforce each other. This is why astronomers looking at cosmological simulations see a universe that becomes progressively more extreme over time. The filaments become thinner and denser, concentrating their matter into tighter and tighter structures. The voids become larger and emptier, occupying more and more of total cosmic volume. And the rate of this increasing contrast is itself increasing, because dark energy is not constant. Its influence is growing relative to the gravitational forces trying to hold structure together. The universe is sorting itself out, and it has been doing so for 14 billion years with no sign of stopping. So when you find a void that appears more empty than your models predict, more empty than the initial quantum fluctuation, and 14 billion years of drainage should be able to produce, the question worth asking is, has something else been helping? Part 8. The Cosmic Web Reality Check. By now you should have a working mental model of the universe's structure. Not the textbook model, not galaxies scattered through space like stars scattered through a galaxy. The real model. Filaments of matter forming a web at cosmological scales. Clusters of galaxies collecting at the nodes where filaments intersect. Walls of galaxies forming flat structures where filaments run parallel. And everywhere else. Everywhere the web does not reach. Voids. Enormous, predominantly empty, continuously growing spheres of organized absence that collectively account for the majority of the universe's volume. This structure has been confirmed repeatedly and from multiple angles. The redshift surveys of the 1980s and 90s, the CFA redshift survey, the Las Campanas redshift survey, the 2-degree field galaxy redshift survey, all showed the same foam-like pattern. The Sloan Digital Sky Survey, launched in 2000 and began returning data in 2003, mapped hundreds of millions of galaxies and produced what remains the most detailed 3-dimensional map of the observable universe ever created. Every major survey, conducted with different instruments, different methodologies, and different sample regions, converged on the same picture. The cosmic web is real, and the voids are its dominant feature. The theoretical underpinning is equally solid. Cosmological simulations, computational models that start with the initial conditions measured from the cosmic microwave background and run the laws of physics forward for 14 billion years, reproduce the cosmic web in remarkable detail. They produce filaments, clusters, walls, and voids in proportions and configurations that closely match what is observed. The standard model of cosmology, lambda CDM, which combines dark energy and cold dark matter with general relativity and inflationary theory, generates a universe that looks, at large scales, extremely similar to the one we actually inhabit. So the foundation is solid, the framework is well tested. The basic picture, quantum fluctuations, inflation, gravitational sorting, dark energy acceleration, foam-like structure, works. For the typical void, the story is understood, and yet the data also contains outliers. The cosmic web is not perfectly reproduced by the simulations in every detail. There are regions that appear more extreme than the models comfortably predict. There are voids that are larger, more empty, or more structurally unusual than the standard model generates in its outputs. Not in ways that break the model entirely, not in ways that physicists are ready to call definitively anomalous, but in ways that raise the kind of quiet, persistent questions that tend to matter in the long run. The most famous of these outliers has a name. It was discovered in 1981. It sits in the direction of a constellation that ancient astronomers name for the herdsman, the figure who drives the bears around the celestial pole. We have been circling it since the beginning of this story. It is time to go in. Part 9. Discovery of Absence. In 1981, a group of astronomers led by Robert Kirshner was conducting a galaxy redshift survey. The work was routine by the standards of the time, measuring the distances to galaxies, plotting their positions, gradually filling in the 3-dimensional map of the universe in the direction of the constellation Boötes. This was painstaking work in the pre-digital era, relying on photographic plates and manual measurement. But the survey was systematic and the team trusted their process. What they found was not what they expected. In a region of sky they had surveyed with reasonable completeness, at the distances they had measured, there were almost no galaxies, not fewer galaxies than average, not a sparse region, a gap, a hole in the distribution of galaxies that stretched across an angular extent far larger than any known structure at the time had any right to occupy. The researchers checked for errors, they checked their redshift measurements, they checked for selection effects, systematic biases in which galaxies were observable and which were not. Everything checked out. The galaxies were not there because the galaxies were not there. The void they had found was real, and it was enormous. Initial estimates put it at roughly 300 million light-years across. Subsequent surveys refined that number in both directions. More careful mapping eventually settled on a diameter of approximately 250 to 330 million light-years, depending on exactly where you draw the boundary of the underdense region. To put that in a context that will stick with you, in a random volume of that size taken from the average universe, you would expect to find somewhere between 2,000 and 3,000 galaxies. The surveys of the Boötes void found approximately 60 galaxies in a volume that should contain thousands. That is a matter presence of roughly 3% of the expected value. 97% of the expected galaxies are simply not there. Initial reactions in the cosmological community varied. Some astronomers were skeptical. The surveys of the time had limitations. the void might not be as empty as it appeared. Later and more complete surveys would surely find more galaxies hiding in the undersampled regions. But the later surveys did not help. Every subsequent observation of the Boötes region confirmed the original finding, often with slightly revised numbers but always with the same fundamental conclusion. This region is dramatically, anomalously, profoundly underdense compared to the cosmic average. The Boötes void became a benchmark. When cosmologists discuss extreme underdensity, Boötes is the reference point. When simulations generate unusually empty regions, they are compared to Boötes. When papers on cosmic voids want to anchor their work to an observational reality that readers will recognize, they cite Boötes. It is, in the vocabulary of modern cosmology, the canonical example of a structure that sits at or beyond the edge of what the standard model comfortably produces. Not beyond the model's theoretical limits, not impossible, not a falsification, just uncomfortable. Just the kind of result that a theorist looks at and says quietly that it is at the high end of what they would expect to see in a universe like this. Part 10. A void, almost without galaxies. 250 million light-years. Let us sit with that number for a moment before moving on, because the tendency with numbers this large is to hear them and immediately let them pass through the mind without sticking, absorbed into the general category of very large space things, without triggering any real sense of magnitude. The distance from one side of the Boötes void to the other is 250 million light-years. Our entire Milky Way galaxy is about 100,000 light-years across. You could line up 2,500 Milky Ways, edge to edge, and they would just barely span the Boötes void. 2,500 of our entire galaxy, arranged in a line, just across the emptiness once. Inside that volume, the survey count stands at approximately 60 galaxies. 60. In a region where standard cosmological models predict somewhere between 2,000 and 3,000. This is not a statistical fluctuation. This is not the expected tail of a probability distribution being sampled at the extreme end by chance. The probability of finding a region this large and this empty in a universe produced by standard inflationary cosmology is, depending on who you ask and which simulation you run, somewhere between vanishingly small and extraordinarily unlikely. The exact figures are debated. Different papers use different boundary definitions for the void, different model assumptions and different statistical tests. But the consistent takeaway across the literature is that the Boötes void is a statistical outlier, not impossible, not a smoking gun, but the kind of outlier that keeps appearing in the data and refuses to be explained away by better measurements. What makes Boötes particularly interesting, and we will come back to this in a way that will make you uncomfortable, is not just its emptiness in aggregate. It is the distribution of the 60 or so galaxies that are there. They are not randomly scattered through the void's interior the way you might expect even a low-density region's galaxies to be scattered. They form patterns, not random distributions, structures within the structure. Arrangements that suggest something interesting happened inside this void that is not captured by the simple model of gravitational drainage over time. The galaxies inside the Boötes void appear to be arranged in something resembling tubes or chains, linear structures within the emptiness, remnants of what might have once been filaments, partially drained but not fully evacuated, leaving behind these skeletal threads of matter in an otherwise emptied space. If that interpretation is correct, it means the Boötes void is not simply a region that started underdense and drained over time. It may be a region where multiple smaller voids merged, their boundaries colliding and merging the way soap bubbles merge, leaving behind the fossils of their previous internal structure in the distribution of the surviving galaxies. That is a subtle but important distinction. A single drained void and a merged complex of smaller voids look similar from the outside but have different internal histories. And the history matters because it tells you something about the process that created the emptiness. The more complex the history, the harder it is to fully account for the final state using only the standard model's parameters. Part 11. The No Other Galaxies scenario. Here is a thought experiment that cosmologists actually use, not as a formal scientific tool, but as a way of communicating viscerally and personally what it means to live inside a void rather than on the edge of one. Imagine that the Earth, the Sun, the entire Milky Way are not where they actually are. Imagine that by some hypothetical cosmic relocation, our galaxy has been placed at the centre of the Botha's void, not near the edge, not in the outskirts where the boundary filaments might be distantly visible, at the geometric centre, at the deepest point of the emptiness. What would the night sky look like? To the naked eye, nothing would change. The stars of the Milky Way would be there. The familiar constellations would be there, because those are nearby stars, and nearby stars are not affected by our position in the large-scale structure. The moon would be there. The planets would be there. Everything within our own galaxy would look exactly the same as it does from here. But look further. In our actual universe, the Andromeda Galaxy is visible to the naked eye as a faint smear of light in the constellation Andromeda. The large and small Magellanic Clouds are visible from the southern hemisphere. With binoculars, dozens of other galaxies become detectable. With a small telescope, hundreds. With the kinds of amateur instruments available today, thousands. The universe, even at modest magnification, reveals itself as a universe, a space filled with other galaxies in every direction. From the centre of the Botha's void, that would not happen. Not because the instruments would fail, because there would be almost nothing to see. The nearest neighbouring galaxies would be tens of millions of light years away, at the void's boundary, too faint to see with anything less than serious observational hardware. The universe, from that vantage point, would appear to consist of the Milky Way and empty darkness. Even with basic telescopes, the kind of instruments that enabled Galileo to see the moons of Jupiter and helped astronomers in the 1800s catalogue thousands of stars, you would see nothing beyond your own galaxy for hundreds of millions of light years in most directions. Now here is the part that really matters. The light from the nearest galaxies at the Botha's boundary takes roughly 100 million light years to reach the centre. That means that even with the right technology, you would not be seeing the galaxies as they are now. You would be seeing them as they were 100 million years ago, and that assumes you have instruments capable of detecting light that has travelled 100 million light years through a nearly empty void. Practical detection capabilities, depending on era, might require instruments far beyond what early astronomers had. Civilizations that developed inside the Botha's void and reached the level of astronomical sophistication we had in, say, the early 20th century might have concluded correctly, given their observational data, that the universe consists of one galaxy, that the Milky Way is everything, that beyond its edges there is simply nothing. That cosmological questions about scale and structure and the distribution of matter across the universe are meaningless because from their vantage point there is no universe-scale distribution to observe. They would have been wrong, of course. The other galaxies are there, clustered in the filaments at the void's edge, invisible only because of distance and darkness. But here is the part that connects back to the central question of this story. If a civilization in a void cannot see other galaxies, what else might be invisible to us from our vantage point? What structures, what presences, what arrangements of matter are hiding, not because they are absent, but because we are looking from the wrong angle? Part 12. The strange geometry inside. The 60 or so galaxies inside the Botha's void are not just anomalous in their number. Their arrangement is strange enough to warrant its own consideration. As mentioned earlier, the surviving galaxies in the void's interior are not randomly distributed. They appear to cluster in linear or tubular arrangements, threads of matter crossing the emptiness that look less like the random survivors of gravitational drainage and more like the remnants of former structure. Former filaments partially consumed. Former boundaries between smaller voids now collapsed into linear traces of what the void's interior once looked like before it became as empty as it is today. This internal geometry is consistent with what is called the void merger hypothesis. In this model, the large void we call Botha's is not a single, primordial, underdense region. that expanded and emptied over time. It is the product of multiple smaller voids growing independently for billions of years, their boundaries eventually meeting, the barriers between them dissolving as matter drained from both sides, the separate voids merging into a single larger structure. The linear galaxy chains we observe today would be fossils of those former boundaries, places where two void interiors met, where the last of the matter between them was concentrated before it too drained away. If this model is correct, it makes the Bhuta's void less of a single anomaly and more of a natural endpoint of the void evolution process. Several average voids that happen to be adjacent grew by the standard processes and merged into one larger structure. That is more comfortable for the standard model. A cluster of ordinary voids producing one very large void is easier to accommodate than a single void that was inexplicably extreme from the beginning. But it does not fully dissolve the anomaly. The question of whether the final merge structure is still larger and emptier than the standard model predicts, even accounting for merger dynamics, remains open. And the internal structure, the specific pattern of the galaxy chains, their geometry, their spacing, is not fully explained by merger models alone. There are patterns in the emptiness that remain, as of the current state of the literature, incompletely understood. This matters beyond Bhuta specifically. Every void is a window into cosmic history. The shape of its interior, the distribution of whatever matter remains inside it, the arrangement of its boundaries relative to neighbouring structure, all of this carries information about how the void formed, how long it has been evolving, and what processes have been acting on it. In most voids, that information is consistent with the standard model's predictions. In Bhuta's, the information keeps asking questions that the standard model answers only partially. There is something here that science is honest enough to acknowledge without yet being able to resolve. And in that unresolved space, in the gap between what the standard model predicts and what Bhuta's actually shows, lives the possibility that forces the most uncomfortable question of all. What if not everything that empties a void is physics? Part 13. The void we live inside. Here is something that significantly changes the context of everything you have just heard. You're not reading about cosmic voids from a safe, well-positioned vantage point outside them. You're not sitting in a typical filament region, inside a dense cluster, surrounded by a representative sample of the universe's matter content. You are, by most current estimates, sitting inside a void yourself. The structure is called the KBC void. Its full name is the Keenan-Barger-Cowie void, after the three astronomers who characterized it in a 2013 paper, and it is, by most measurements, the largest identified void in the observable universe, approximately 2 billion light-years across. 2 billion light-years. Recall that the Bhuta's void, the structure we just spent considerable time examining, is roughly 250 to 300 million light-years in diameter. The KBC void is roughly 6 to 8 times larger in diameter than Bhuta's, and because volume scales as the cube of diameter, the KBC void is roughly 200 to 500 times larger in volume than Bhuta's. It is so large that the Bhuta's void could fit inside it with enormous room to spare, and our galaxy, the Milky Way, the Local Group, the Virgo cluster, the entire structure known as Laniakea supercluster, sits near its centre. Let that sink in. The supervoid we are most familiar with, the one whose effects most directly shape our cosmological measurements and our observations of the large-scale universe, is the one we live inside. We are not outside observers looking at the universe's emptiness. We are embedded in it. Our view of the cosmos is being filtered through a 2 billion light-year sphere of underdensity, and we're still in the early stages of understanding how that affects what we think we know. The implications are significant. A galaxy inside a void experiences slightly different gravitational conditions than a galaxy in a typical filament region. It is being pushed outward by the void dynamics, flowing toward the surrounding overdensities at the void's boundary. Other galaxies near the void's centre are flowing in the same direction. This collective flow, called bulk flow, is measurable, and when astronomers measure it, they find something interesting. The local group and its neighbours appear to be flowing outward from the void centre at a rate consistent with the KBC void's size and underdensity. This is not a small effect. It is a measurable, ongoing consequence of living inside a structure that is actively pushing matter toward its boundaries, and it raises the question of how much our position inside this enormous emptiness is colouring our view of everything else. Part 14. The expansion measurement problem. For the past decade or so, cosmology has had a quietly escalating crisis. It goes by the name Hubble tension, and if you're not already familiar with it, here is the core problem. The Hubble constant is the number that describes how fast the universe is expanding. It is usually expressed in units of kilometers per second per megaparsec. That is, how fast a galaxy 1 megaparsec away is receding from us due to cosmic expansion. The problem is that two independent methods of measuring this number produce two different answers, and they disagree with each other at a level of precision that makes simple measurement error an insufficient explanation. The first method looks at the early universe. By analysing the cosmic microwave background, the ancient light released 380,000 years after the Big Bang, which has been mapped with extraordinary precision by satellites like WMAP and Planck, cosmologists can infer the Hubble constant from the physics of that early epoch. The value they get is approximately 67 kilometers per second per megaparsec. The second method looks at the local universe. By using distance ladders, chains of measurement that start with nearby stars and extend to distant supernova, cosmologists measure how fast nearby galaxies are actually moving and derive the Hubble constant from direct observation. The value they consistently get is approximately 73 kilometers per second per megaparsec. 67 versus 73. That sounds like a small difference. It is not. In cosmological terms, it represents a 5 sigma discrepancy, a level of disagreement that, in physics, is the threshold for declaring a discovery. Something is different between the early universe prediction and the local measurement, and whatever that something is, it is not explained by known physics. One possibility that has attracted genuine research interest is the KBC void. If the Milky Way is inside a large underdense region, then the local measurement of cosmic expansion might be slightly biased. Galaxies near the void centre, including ours, are flowing outward, boosted by the void's gravitational dynamics in addition to the cosmological expansion. If that local bulk flow is not fully accounted for, the local Hubble constant would appear slightly inflated compared to the cosmic average. This is not a confirmed solution to Hubble tension. The void explanation has been modelled, and some papers suggest it can account for part of the discrepancy. Others conclude the KBC void is not large enough or deep enough to explain the full 5 sigma gap. The debate is ongoing, but the point, for our purposes, is this. The void we live in is not a passive backdrop. It may be actively distorting our measurement of the universe's most fundamental property, which means that our understanding of how fast the universe is expanding, how old it is, and what it will look like in the far future may be slightly, or perhaps not so slightly, coloured by the specific emptiness we happen to live inside. Part 15. The Cold Spot Mystery. In 2004, a team of astronomers analysing data from NASA's WMAP satellite, the Wilkinson Microwave Anisotropy Probe, a spacecraft designed to map the cosmic microwave background with unprecedented precision, found something in the data that did not belong there. Or rather, they found something that was conspicuously absent. In a region of sky in the direction of the constellation Eridanus, the CMB appeared colder than the surrounding sky by a statistically anomalous amount. Not dramatically colder, not the kind of difference that jumps off a chart and announces itself. The variation was approximately 70 microkelvin below the average temperature of the cosmic microwave background, 70 millionths of a degree. In absolute terms, a number so small it is essentially unfelt by any physical process at human scales. But in the language of the cosmic microwave background, 70 microkelvin is not a small number. It is a loud one. To understand why, you need to understand what the CMB actually is and why its temperature variations matter so much. The cosmic microwave background is the oldest light in the observable universe, radiation released approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing photons to travel freely rather than being constantly scattered. That light has been travelling ever since. It reaches us from every direction simultaneously, a perfect sphere of ancient radiation surrounding us at a distance of approximately 46 billion light-years, carrying within its temperature variations a detailed record of the density fluctuations that existed in the early universe. Slightly hotter regions correspond to slightly denser regions in the early universe. Slightly cooler regions correspond to slightly less dense ones. The variations across the entire CMB sky are extraordinarily small, on the order of 1 part in 100,000. The universe was remarkably smooth in its early moments. But that smoothness is not perfect, and the pattern of imperfections is not random. It carries information. It is, in the most literal sense, a baby picture of the universe, a snapshot of the density landscape that would, over billions of years, be amplified by gravity into the cosmic web we observe today. Cosmologists study it with the same intensity that a doctor studies a patient's genetic profile, because it contains the seeds of everything that came after. Against that backdrop of 1 in 100,000 variations, a 70 microkelvin cold spot in a localized region of sky is not subtle. It corresponds to a density variation in the early universe significantly larger than standard inflationary models comfortably predict for a region of that angular size. The models allow for fluctuations. They expect fluctuations. But a fluctuation this large, in a region this big, sits at the uncomfortable end of the probability distribution, the kind of result that makes cosmologists reach for their error analysis software and start checking their assumptions. The WMAP team checked their assumptions. They checked for instrumental artifacts, systematic errors introduced by the satellite's detectors, or scanning pattern that might produce a false cold region. They found none. They checked for foreground contamination, emission from gas or dust in our own galaxy, that might be interfering with the CMB signal in that direction. The corrections were made, and the cold spot persisted. They checked the statistical significance, debated the appropriate way to calculate it given that you're looking at a full sky map and can always find the coldest spot on any map by definition. Even accounting for that, the cold spot remained anomalous, not impossible, not a definitive falsification of the standard model, but persistent and stubbornly resistant to easy explanation. In 2013, the Planck satellite, the European Space Agency's follow-up to WMAP, with significantly better sensitivity and angular resolution, re-examined the same region of sky with more precise instruments and a more complete analysis. The cold spot was confirmed. It was real. It was not an artifact. Whatever was producing it, or whatever had produced the early universe density variation that it recorded, was a genuine feature of the CMB and not a measurement error. One explanation attracted considerable attention, both because it connected naturally to the large-scale structure observations being made simultaneously, and because it provided a concrete physical mechanism rather than just a statistical shrug. The hypothesis was that a supervoid lies along the line of sight to the cold spot, positioned between us and the surface of last scattering, the spherical shell from which the CMB photons were emitted. A supervoid large enough and empty enough sitting in exactly the right location along that line of sight could in principle imprint a cold signature on the CMB through a mechanism called the integrated Sachs-Wolf effect. The physics of the integrated Sachs-Wolf effect is subtle, but not complicated once you have the basic picture. Light travelling through space is affected by the gravitational environments it passes through. When a photon falls into a gravitational well, a dense region, a cluster, a filament, it gains energy. When it climbs out of that well, it loses the energy it gained. In a static universe, these two effects cancel out perfectly, and the photon emerges with the same energy it had before entering the well. But we do not live in a static universe. The universe is expanding, and in an expanding universe, a void, which is a kind of negative gravitational well, a region of below average density, behaves asymmetrically for passing photons. A photon entering a void is, in a sense, climbing out of the surrounding structure into a region of lower density. It expends a small amount of energy doing so. As it crosses the void interior, the void is expanding. It is physically larger when the photon exits than when it entered, because the universe has expanded during the crossing time. When the photon exits the void on the far side, the gravitational landscape it re-enters is slightly different from the one it left, because the expansion has changed the geometry. The result is a net energy loss. The photon emerges from the void very slightly less energetic than it was when it entered. Less energy means longer wavelength. Longer wavelength in the CMB means lower apparent temperature. A large supervoid along the line of sight to a CMB region would produce, through exactly this mechanism, a cold spot in the observed CMB temperature map. This is not speculative physics. The integrated Sachs-Wolfe effect is a well-established prediction of general relativity in an expanding universe. It has been measured statistically in correlations between CMB temperature maps and galaxy survey maps. The mechanism is real. The question is not whether it operates, but whether it operates at the scale required to explain the Eridanus cold spot. In 2015, a team led by Istvan Sapudi at the University of Hawaii confirmed the existence of the Eridanus supervoid, a genuine underdense region in the direction of the cold spot, extending across approximately 1.8 billion light-years and representing a matter deficit of roughly 20% below the cosmic average. It was real, it was large, it was positioned, at least approximately, along the line of sight to the cold spot. The integrated Sachs-Wolfe explanation had its candidate structure. But the debate did not close, it shifted. The question moved from whether the supervoid existed to whether it was sufficient, whether a void of the measured size and depth could produce a temperature decrement as large as the observed cold spot through the integrated Sachs-Wolfe effect alone. And here the models ran into friction. Most analyses concluded that the Eridanus supervoid, as characterized by the available survey data, could account for perhaps a portion of the cold spot's temperature anomaly. Some papers suggested around 50%, others less. The remainder required either a deeper void than the surveys had found, or a statistical fluctuation in the primordial CMB itself, or some additional physical mechanism not currently in the standard model. The supervoid is there. The cold spot is there. They're in roughly the right relationship to each other, and the explanation is incomplete. This incompleteness matters beyond the specific case of Eridanus, because it illustrates something that keeps surfacing from multiple directions in the study of cosmic voids. The voids are not passive. They are not simply regions of space that matter left behind, sitting quietly while the rest of the universe evolves. They interact. They leave fingerprints. A void large enough and empty enough reaches across hundreds of millions of light years to alter the temperature of light that has been travelling since 380,000 years after the Big Bang. It subtracts energy from photons that are older than any structure in the observable universe. It writes its signature into the oldest record we have of the cosmos's earliest moments, and some of those signatures do not fully add up. The cold spot is older than the Eridanus supervoid by billions of years, imprinted when the universe was still nearly featureless. The supervoid formed later through gravitational drainage and dark energy expansion over billions of years of cosmic evolution. The two structures are causally connected only in the sense that the same early universe density variation that eventually became the supervoid also left its mark on the CMB. But the cold spot appears larger and colder than the supervoid, as currently measured, would fully explain. Something in the accounting does not balance. That imbalance is either a measurement limitation, the surveys do not go deep enough, the void is emptier than we have measured, the models of the integrated Sachs-Wolf effect are missing a correction factor, or it is a genuine residual that points toward physics we do not yet have. Both possibilities are scientifically interesting. The first is reassuring in the way that known unknowns are reassuring. The second is not reassuring at all, because it means the oldest light in the universe is carrying a message we cannot yet fully read. Emptiness is doing things. Not metaphorically, physically, measurably, in the data. And some of what it is doing does not yet have a complete explanation, which, given everything else we have covered in this story, feels less like a footnote and more like a pattern. Part 16, the local void and the near darkness. Before we move into the most speculative territory of this discussion, it is worth pausing to establish something that tends to get lost when cosmology operates at the scales we have been discussing. The void structure we have been mapping and analysing and finding anomalous is not a distant phenomenon. It is not something that exists only in the deep survey data, visible only to instruments sensitive enough to detect galaxies billions of light years away. The large-scale emptiness of the universe is not out there, somewhere beyond the reach of anything that matters to our immediate cosmic situation. It is here. It begins, in the most literal geographical sense, at our doorstep. The local group is the gravitationally bound cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller satellite galaxies scattered around them. It is our immediate cosmic neighbourhood, the collection of galaxies close enough to each other that their mutual gravity dominates over the universe's expansion, binding them together into a structure that will persist and eventually merge rather than drift apart. The Milky Way and Andromeda are, in fact, on a collision course, expected to begin their merger in approximately 4.5 billion years, which is either concerning or irrelevant depending on your planning horizon. The local group sits within a larger structure called the Virgo supercluster, which is itself one lobe of an even larger structure called Laniakea, a supercluster complex stretching across approximately 500 million light-years that was only fully mapped and named in 2014, when a team led by Brent Tully used galaxy velocity flows to define its boundaries. Laniakea contains approximately 100,000 galaxies and has a total mass of roughly 10 to the power of 17 solar masses, a number that means essentially nothing in human terms, but represents one of the largest coherent structures in the observable universe. And at the edge of the local group, at the boundary where our gravitationally bound neighbourhood ends and unbound space begins, the local void starts. The local void extends for roughly 200 million light-years in the direction away from the Virgo cluster. It is not as dramatically empty as the Bhuta's void. Its underdensity is significant, but not at the extreme end of the void spectrum, and it is not as geometrically enormous as the KBC supervoid that surrounds us on a larger scale. By the standards of the catalogued void population, it is a mid-size structure, unremarkable in the context of cosmic statistics. But it is immediately adjacent to us in a way that no other large void is. It does not require a deep survey to find. It does not require redshift measurements of distant galaxies to characterize. It is the emptiness that begins where our neighbourhood ends, extending outward in one direction for 200 million light-years while the Virgo filament extends in roughly the opposite direction into denser structure. Think about what that means in terms of the view from our position. If you could somehow step outside the local group and look back at it from a sufficient distance, from a vantage point high enough above the cosmic web to see both our cluster and the surrounding structure simultaneously, the way you might look at a coastline from altitude, the geometry would be immediately apparent. On one side, the Virgo direction, you would see structure, filaments converging, galaxy clusters accumulating at their intersections. The cosmic web building up in the direction of overdensity, matter concentrated along threads that connect to larger and larger nodes of gravitational accumulation. It would look, from that altitude, like the edge of a continent, complicated, active, structurally rich, full of features at every scale. On the other side, the local void direction, you would see something entirely different. The filaments thin almost immediately, the galaxy density drops. Within a relatively short cosmological distance from the local group boundary, the structure essentially disappears, replaced by the 200 million light-year expanse of below-average density that constitutes the local void, which itself blends into the larger underdensity of the KBC supervoid surrounding us on all sides. From that external vantage point, our galaxy cluster would look exactly like what it is, a coastal settlement. A concentration of structure sitting at the edge of an ocean of emptiness, with civilization, in the cosmic sense, meaning matter and galaxies and everything built from them, concentrated on one side and open, largely featureless space extending in the other direction for distances that dwarf the structure itself. We are edge dwellers, not metaphorically, not poetically. Literally in the three-dimensional geometry of the large-scale universe, our galaxy is positioned at the boundary between a region of above-average density and a region of below-average density, and has been for as long as the local group has existed as a gravitationally bound structure. This is not a coincidence in any meaningful sense. Most galaxies, given the foam-like structure of the cosmic web, are near the boundaries of voids rather than deep inside them, because that is where the filaments are, and filaments are where galaxies form. But it does mean that the void is not abstract for us. It is directional. It is the specific direction we are currently moving away from, as the local group flows toward the Virgo overdensity and away from the local void's evacuating interior. That flow is measurable. The local group is moving at approximately 630 kilometers per second relative to the cosmic microwave background rest frame. Part of that motion is the well-known pull toward the Great Attractor, the massive overdensity in the direction of the Centaurus constellation that has been drawing our galaxy and its neighbours for billions of years. But part of it is also the push. Voids do not just passively lose matter, they actively, in the sense that gravity actively operates, push matter toward their boundaries. The lower density inside the void means weaker gravitational pull from the void's interior, which means the net gravitational force on galaxies at the void's edge points outward toward the surrounding filaments. We are being pushed as well as pulled. The local void is at this moment contributing to the velocity of the Milky Way through space by effectively repelling us toward higher density regions. This has been confirmed observationally. In 2017, research led by Yehuda Hoffman and collaborators used peculiar velocity data, measurements of how galaxies move relative to the pure Hubble flow expansion, to map the gravitational influences on the local group's motion. The local void appeared as a genuine repeller in the analysis, a region whose below-average density was producing a measurable outward push on surrounding galaxies, including our own. The void is not passive, it is acting on us, right now, in a way that contributes to our motion through the universe at hundreds of kilometers per second. Layer onto this our position inside the KBC supervoid, the 2 billion light-year structure that surrounds the local group on all scales, larger than the local void itself, and the picture becomes one of genuine multi-scale embeddedness in emptiness. We are not near a void. We are not adjacent to a void in the way that one city is adjacent to another. We are inside multiple nested underdense structures simultaneously, each one operating at a different scale, each one contributing to the gravitational and kinematic environment that our galaxy experiences, each one potentially influencing the cosmological measurements we make from our position within them. The KBC void, as discussed earlier, may be contributing to the Hubble tension, the disagreement between locally measured and globally inferred expansion rates that has resisted resolution for over a decade. The local void is contributing to our peculiar velocity, the component of our motion through space that is not explained by simple cosmic expansion. The cold spot in the CMB, in the direction of Eridanus, may be the fingerprint of yet another large underdense structure along a different line of sight. From every direction we look, at every scale we probe, the emptiness is present, active, and in several cases producing effects we have not yet fully characterized. And yet despite all of this, despite the local void at our doorstep, the KBC supervoid surrounding us, the measurable push of evacuating space on our galaxy's motion, the potential influence on our most fundamental cosmological measurements, the void remains, in the public understanding of the universe, an afterthought. The background, the space between the interesting things. This framing has it precisely backwards. The voids are not the space between the interesting things. The voids are the dominant structure. Everything else, every galaxy, every star, every planet, every civilization that has ever existed or could ever exist in the observable universe, occupies the thin, fragile, gravitationally concentrated boundaries of structures whose interior is organized emptiness. We are the afterthought, the voids are the main event, and we have been living inside one, moving through one, being shaped by one, for the entire history of our existence without fully registering what that means, which brings us finally to the territory where the known physics ends and the genuinely open questions begin. Because if the voids are this active, this influential, this structurally dominant, and if our best models still cannot fully explain the most extreme of them, then the question of what they actually contain, or do not contain, or have been arranged to appear not to contain, becomes not a fringe speculation, but a legitimate frontier. The emptiness is real, its effects are measurable, its anomalies are documented, and its ultimate nature, whether it is genuinely empty or merely appears that way from where we stand, remains, as of everything we currently know, an open question, which is either deeply unsatisfying or the most exciting sentence in cosmology, depending on your temperament. Part 17. The Fermi Paradox Reframed. The universe is approximately 13.8 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. A significant fraction of those stars have planets. A significant fraction of those planets orbit in the habitable zones where liquid water can exist. Even under conservative assumptions, the number of planets in the observable universe capable of supporting life is a number with more digits than you would want to write out. We're not talking about thousands of candidate worlds. We're not talking about millions. We're talking about a number so large that if you started reading it aloud right now, you would still be reading when the sun exhausts its hydrogen fuel and swells into a red giant. And yet we have heard nothing, detected nothing, observed no unambiguous evidence of any intelligence beyond our own planet in the entire history of human observation. Not a signal, not a structure, not a pattern in the noise that could not be explained by natural processes. Decades of radio telescope surveys, from the first formal SETI searches in the 1960s, all the way through the sophisticated multi-frequency scans running today, have returned nothing that survives scrutiny. One candidate signal, the famous WOW signal detected in 1977, lasted 72 seconds and was never detected again despite repeated attempts to find it at the same coordinates. The rest is silence. Clean, unbroken, universe-wide silence. This is the Fermi paradox, named for the physicist Enrico Fermi, who posed a version of the question at a lunch table in 1950. The story goes that Fermi and a group of colleagues were discussing the possibility of extraterrestrial life over lunch, when Fermi, apparently out of nowhere, asked a question that stopped the conversation. Where is everybody? Not as a rhetorical flourish, as a genuine calculation. The universe is old enough, large enough, and apparently hospitable enough that if life and intelligence emerge with any reasonable frequency, the universe should by now contain civilizations billions of years old, with billions of years of technological development behind them. A civilization with even a modest head start on us, say 1 million years, which is less than 1/100th of 1% of the universe's current age, would have had time to spread across the galaxy many times over, even at speeds far below the speed of light. Where are the signals? Where are the megastructures? Where is the evidence that anyone, anywhere, ever made it past the stage we are currently at? The question remains open. It has been open for 75 years, and the silence has only gotten louder as our instruments have improved. The standard answers are well rehearsed at this point. Life is rare. Perhaps the chemistry required for biology is far more improbable than we assume, and Earth represents a statistical miracle rather than a typical outcome. Intelligence is rarer still. Perhaps complex multicellular life is common enough, but the leap to self-awareness, language, technology, and civilization is an almost impossibly narrow bottleneck that most life never clears. Interstellar travel is too hard. Perhaps the physics of moving between stars is so prohibitively expensive in time and energy that no civilization, regardless of how advanced, ever manages to spread beyond its home system. And then there is the darkest standard answer, the one that gets called the Great Filter. Perhaps civilizations routinely destroy themselves before reaching the technological threshold required to become visible across interstellar distances. Nuclear weapons, climate collapse, engineered pathogens, artificial intelligence. Some self-terminating mechanism that every civilization encounters and almost none survive. All of these answers are possible, some are plausible, none are definitively supported or ruled out by current evidence. We do not have a large enough sample of civilizations to do statistics on civilizational survival rates. We have exactly one data point, ourselves, and we are still in the early chapters. The question remains open in the most uncomfortable possible way, the kind of open that does not feel like an invitation to curiosity, but like a door that should have something behind it and does not. But there is a reframing of the Fermi paradox that connects directly to everything we have discussed in this story, and it is more disturbing than any of the standard answers. Not because it requires exotic physics or unfamiliar mathematics, because it requires almost nothing. Just a change of assumption so simple, it is almost embarrassing that it does not come up more often in serious discussion. The reframing is this. What if we are not detecting civilizations not because they are absent, but because we cannot see them? What if the universe contains exactly what the Fermi paradox suggests it should contain? Ancient, advanced, galaxy-scale civilizations, but our detection capability is fundamentally limited in a way we have not yet fully accounted for. What if the silence is not an absence of signal, but a failure of receiver? And what if voids are the answer to why? Think carefully about how we detect civilizations at interstellar or intergalactic distances. We look for light. We look for radio emissions, the kind that leak from planetary civilizations as a byproduct of broadcasting technology. We look for infrared excess, the kind of thermal signature that might indicate energy being collected at large scales and re-radiated as waste heat. We look for laser pulses, for anomalous spectral lines, for any pattern in the electromagnetic spectrum that departs from what natural astrophysical processes would produce on their own. Our entire search strategy, every dollar spent on SETI, every telescope pointed at candidate stars, every algorithm designed to sift signal from noise, is predicated on a single foundational assumption: that advanced civilizations are detectably luminous, that they glow, that they leak, that they radiate in ways that differ from stars and gas and dust in ways we can identify from here. That assumption has never been seriously questioned, because for a civilization at our level of development it is obviously true. We are detectably luminous. Our radio emissions have been expanding outward at the speed of light since the early 20th century, forming an expanding sphere of signal, now roughly 200 light-years in radius. Any civilization within that radius with equipment comparable to ours could detect us. We glow, we leak. We are electromagnetically loud in the way that all young, energy and efficient civilizations are loud. But a civilization 1 million years older than us would not necessarily still be loud. It might have learned, out of pure engineering efficiency, to stop leaking. A civilization that has mastered large-scale energy collection does not waste photons. It captures them. It uses them. Every photon that escapes into space is a photon that did not do useful work, and a civilization optimizing its energy budget at galactic scales would minimize escape. The older and more efficient a civilization becomes, the quieter it becomes. Not because it is hiding necessarily, but because wasting energy is for beginners. And voids already appear electromagnetically quiet. They contain almost no galaxies, which means almost no stars, which means almost no natural light sources. They are already, by definition, regions where our standard detection methods return near zero signal. The noise floor inside a void is vanishingly low. If something existed inside a void, if a civilization had established itself inside a void, for whatever reason, the baseline against which we would compare its emissions would be nearly zero. A signal that would be easily detectable against the bright background of a filament region might be completely invisible against the near-perfect darkness of a supervoid interior. The signal-to-noise challenge is not just different inside a void, it is categorically, fundamentally different in ways that our current detection strategies were never designed to address. We built our search instruments to find bright things against bright backgrounds. We scan the filaments, the clusters, the galaxy-rich regions where the density of candidate civilization should be highest. We point our dishes at stars. We analyze the spectra of nearby planetary systems. We do all of this in the places where the universe is fullest, brightest, and most structured. And we systematically, almost by design, ignore the places where the universe is emptiest. This is not yet speculative. This is just statistics and geometry and the logic of where we have and have not looked. But it prepares the ground for something that is. Because the next question is not whether voids are too dark for our instruments to find a signal inside them. The next question is whether something inside a void might have specifically arranged things so that no signal escapes at all. Not as a byproduct of efficiency, as a choice. And that question belongs to a framework of thinking about advanced civilizations that is going to require us to think much bigger than radio telescopes and spectral anomalies. Part 18. The Kardashev Horizon. In 1964, the Soviet astronomer Nikolai Kardashev published a paper that was, on the surface, a fairly dry exercise in classification. He wanted a framework for thinking about technological civilizations at scales beyond our own, a way of organizing the possibilities that did not rely on assumptions borrowed from human history or science fiction. What he produced was a three-tier scale based on a single variable: energy, not intelligence, not moral development, not the sophistication of art or philosophy or social organization, just energy. How much of it a civilization can access, control, and use. The elegance of the Kardashev scale is that energy is a universal currency. Every physical process in the universe involves energy. Every technology, at every level of sophistication, is ultimately a method of capturing energy from one source and directing it toward a purpose. A campfire and a nuclear reactor are both, in the most fundamental sense, doing the same thing, accessing stored energy and releasing it in a controlled way. The difference is scale and efficiency. Kardashev simply asked, what does that scale look like when you follow it all the way out? A Type 1 civilization harnesses all the energy available on its home planet. Every form of energy from every source, solar, geothermal, wind, tidal, nuclear, chemical, captured and used at full planetary capacity, with nothing wasted and nothing left unharvested. We are currently somewhere around 0.7 on this scale, not even Type 1 yet. We still burn fossil fuels inefficiently, still lose enormous amounts of generated energy to heat waste, still leave vast quantities of solar energy falling on our planet's surface without capturing it. By Kardashev's framework, we're a young, inefficient, early-stage civilization. Promising, perhaps, but not yet graduated to the first rung. A Type 2 civilization harnesses the complete energy output of its home star. The total luminosity of a sun for our own star that is approximately 3.8 times 10 to the power of 26 watts, a number so large it has no useful analogy in human experience, captured entirely and directed toward the civilization's purposes, every photon, every unit of solar wind, every form of energy the star produces, collected before it can escape into space and used for something. This requires engineering at scales we cannot currently build, but nothing about it violates known physics. It is an engineering challenge, not a theoretical impossibility. And a Type 3 civilization harnesses the energy output of an entire galaxy. Hundreds of billions of stars, each one a Type 2 energy source, all of it flowing into a single civilization's infrastructure. A Type 3 civilization does not live on a planet or even a star system. It lives across a galaxy the way a city lives across a landscape, distributed, interconnected, drawing resources from every node in its network simultaneously. Freeman Dyson, a physicist working independently around the same time Kardashev published his paper, had been thinking along similar lines from a different angle. Dyson was interested in a specific engineering question. How would a civilization actually go about capturing a star's entire energy output? His answer was a megastructure, a shell, or more practically a swarm of structures, surrounding a star at a distance roughly equivalent to a habitable orbit, capturing the star's light output before it could escape into space. The structure would absorb the light, use it for whatever purpose the civilization required, and then re-radiate the remaining energy as waste heat at a lower temperature. It would not disappear thermodynamically, energy cannot be created or destroyed, but it would change its character. Instead of visible light radiating outward from a star, you would have a diffuse infrared glow radiating outward from a large, relatively cool structure. This became known as a Dyson sphere, though Dyson himself preferred the term Dyson swarm, acknowledging that a rigid shell around a star would be mechanically implausible, while a swarm of independent collectors in coordinated orbits would not. The concept was taken seriously enough that astronomers have actually searched for Dyson sphere candidates, stars showing anomalous infrared excess relative to their visible output, suggesting that something is intercepting their light. The most famous candidate was the star KIC 8462852, nicknamed Tabby's star, which showed irregular and dramatic dimming patterns that briefly generated considerable excitement before more mundane explanations involving dust clouds gained the upper hand. No confirmed Dyson sphere has been found, but the search itself acknowledges a serious point. If they exist, we might be able to detect them, because the physics of waste heat means they cannot be fully invisible. Now scale this concept up. Not one star, not one solar system, an entire galaxy. A Type 3 civilization building Dyson spheres around every star in its galaxy, or using some equivalent form of mega-engineering to capture the galaxy's total energy output, would progressively darken that galaxy in visible light. Star by star, system by system, the visible luminosity of the galaxy would decrease as each new star was enclosed. From outside the galaxy, the process would look like a dimming. A galaxy that should contain a certain luminosity based on its estimated mass would appear underluminous. The stars would still be there, still burning, still producing energy. But none of that energy would be escaping as visible light. It would all be captured, used, and re-radiated as diffuse infrared emission from the enclosing structures. At full completion, every star enclosed, every photon captured, the galaxy would be invisible to any instrument looking for visible light. It would not appear in optical surveys. It would not contribute to redshift maps that rely on detecting galaxy light. It would appear to any civilization conducting a cosmological survey using optical or radio methods as an empty region of space, a gap, an absence, a void. Let that land for a moment, because it is worth being precise about what is being said here. What would a galaxy fully enclosed by Type 3 infrastructure look like from the outside? It would look empty. It would look, from a cosmological survey perspective, like a region containing fewer galaxies than expected. It would look, depending on how many galaxies had been enclosed and across what volume of space the civilization had expanded, like reduced luminosity across a broad region. It would resemble, in redshift maps and galaxy count surveys, an underdense region. And if the civilization had expanded across multiple galaxies, if it had enclosed not one but dozens, hundreds, perhaps thousands of galaxies within its infrastructure, the region it occupied would look, to every instrument we currently possess, like a supervoid. It would look like a void. And here is where the logical chain becomes important to follow carefully, because this is not hand-waving. This is a step-by-step argument with no broken links. Fully enclosed galaxies produce no detectable visible light. A survey region containing no detectable visible light is recorded as containing no galaxies. A region recorded as containing no galaxies is classified as an underdense region or a void. A sufficiently large region of this kind is classified as a supervoid. This chain is not broken at any link by any known physical principle. The observational outcome of a maximally energy-harvesting Type 3 civilization, expanding across a region of space large enough and enclosing enough galaxies completely enough, would be indistinguishable from a natural cosmic void using any optical or radio instrument currently in operation. There is a partial exception worth acknowledging honestly. The waste heat problem does not fully disappear. A civilization enclosing galaxies must still radiate energy. The laws of thermodynamics do not negotiate. That energy would appear as diffuse infrared emission from the void region. Some researchers have proposed searching for exactly this signature, anomalously warm infrared backgrounds in void regions that cannot be explained by residual natural sources. The search is technically feasible. It has not yet been conducted with sufficient sensitivity to rule the hypothesis in or out. Which brings us to the honest answer about where we currently stand. The question is not whether the technological void hypothesis is proven. It is not. The evidence does not establish it. The question is whether it is distinguishable from the natural hypothesis using current methods. And the answer to that question, stated as plainly as the data allows, is not definitively, not yet. Possibly not ever with instruments built on the assumptions we currently make about what we are looking for. We mapped the voids by their darkness. We confirmed them by the absence of the light we expected to find. We built our entire model of cosmic structure on the assumption that dark means empty. That assumption is physically reasonable. It is statistically well supported for the majority of cases, and it is, in at least the logical sense, unproven for any individual void we have ever catalogued. The darkness is real. Whether the emptiness is real is a different question entirely. And the difference between those two questions is where the most uncomfortable territory in this entire discussion begins. Part 19, Void, Nature or Technology. Here is the core of the most uncomfortable possibility in this entire discussion, stated as plainly as it can be stated. We have two explanations for why a region of space might appear to contain almost no galaxies. Two frameworks, two stories that begin in completely different places and arrive at exactly the same destination. The first explanation is natural physics. It is the standard story, the one that appears in textbooks and journal papers and cosmology lectures at universities around the world. Quantum fluctuations during the inflationary period seeded a region of space with slightly below average density. That initial underdensity was not dramatic. It was a whisper, a fractional variation in energy distribution across a region smaller than an atom, stretched to cosmic scales by the violence of inflation. Gravity then spent 14 billion years doing what gravity does, pulling matter away from low-density regions toward high-density ones, amplifying every difference, draining the underdense region of whatever matter it had, sending that matter flowing outward toward the surrounding filaments. Dark energy accelerated the process, stretching the emptiness faster than gravity alone could manage. The result, after 14 billion years of this patient, relentless, purely physical process, is a supervoid. Enormous, ancient, structurally fascinating, and in this explanation, containing essentially nothing. The absence is real. The emptiness is genuine. It is the product of pure physical processes operating over cosmic timescales, and it requires no additional explanation beyond the standard model of cosmology. The second explanation is something else entirely. A sufficiently advanced civilization, one that has been developing for hundreds of millions or billions of years, rather than the few thousand years of recorded human history, expanding across galactic scales, harvesting the energy output of stars and galaxies through mega engineering we cannot currently design or build would progressively reduce the visible luminosity of the region it occupied, not as a side effect, not as a byproduct, as the direct and inevitable consequence of what it means to be a maximally energy-efficient civilization at cosmological scales. At the extreme end of the Kardashev framework, a civilization operating at Type 3 or beyond would not leak light. It would capture light. It would enclose stars, then star systems, then entire galaxies, wrapping each energy source in infrastructure before the photons could escape. The region it inhabited would grow progressively darker as the civilization expanded. And to an outside observer, a young civilization, say, on the edge of a filament, pointing survey instruments into the void, that region would appear as a dramatic reduction in galaxy counts. An underdense region, a void, indistinguishable with any instrument currently in existence from the natural version. Both explanations produce the same observational signature. Both are fully consistent with what we see, and we currently possess no instrument, no method, no analytical technique that allows us to definitively distinguish between them. Let that sit for a moment, because it is easy to read past it and not feel its full weight. We have catalogued over 8,000 voids in the observable universe, every supervoid, every extreme underdensity, every region where our surveys return near zero galaxy counts. Every one of them is currently classified as natural, because natural is the default, the baseline assumption, the explanation that requires the fewest additional hypotheses. And for the vast majority of those 8,000 voids, the natural explanation is almost certainly correct. The standard model generates void distributions that broadly match observations. The physics is well tested. The simulations reproduce the large-scale structure with impressive fidelity. Most voids are almost certainly just voids. But almost certainly is doing a significant amount of work in that sentence, and the same observational data that supports the natural explanation cannot, in strict scientific terms, exclude the alternative. Not for all 8,000 voids simultaneously, not even for any single individual void. The absence of detected galaxies in a void region cannot be positively attributed to the genuine non-existence of galaxies there. It can only be attributed to the absence of detectable light from that region, and those are not the same thing. A galaxy that emits no detectable light is observationally identical to a region of space containing no galaxy. The instrument cannot tell the difference. The survey cannot tell the difference. The map that results from the survey cannot tell the difference. The two scenarios produce the same data point. Nothing detected here. A civilization that has made its galaxies dark, that has enclosed their stars and captured their light, and redirected every photon toward internal use, is doing so, presumably, because it has something extremely interesting to do with that energy. It is running something, computing something, building something, sustaining something across scales we have no framework to imagine. And whatever it is doing, it is not broadcasting. It is not leaking. It is not doing anything that produces a signal distinguishable from background in the electromagnetic spectrum at the wavelengths we monitor. It has, from our perspective, gone quiet. Not gone. Quiet. There is a distinction worth drawing here between two different versions of this scenario, because they have meaningfully different implications. In the first version, the darkness is incidental. The civilization is not trying to hide. It has simply become so energy efficient, so thoroughly optimized in its use of every available photon, that hiding is an automatic consequence of its normal operations. It is not aware of us, or not concerned with whether we can see it, or has simply never considered the question of its visibility to younger civilizations. The darkness is a byproduct of competence, not a strategy. In the second version, the darkness is intentional. The civilization has chosen to be invisible. Perhaps it surveyed the universe at some earlier stage of its development and concluded that visibility was dangerous, that announcing your presence across cosmological distances to unknown neighbours was not a risk worth taking. Perhaps it encountered something in its expansion that convinced it concealment was the correct long-term strategy. Perhaps it simply prefers privacy at a scale we have no cultural framework to understand. In this version, the void is not just a region where energy is being efficiently used. It is a region where a decision has been made, a deliberate, sustained, civilization-scale decision to remain undetectable. The uncomfortable reality of both versions is identical. They are indistinguishable from the natural explanation using current technology. And this is where the scientific method, which is generally our most reliable tool for navigating exactly this kind of uncertainty, runs into a specific kind of wall. Science works by making predictions that can be tested. A good scientific hypothesis generates expectations about what you should observe if the hypothesis is true, and those expectations differ from what you would observe if the hypothesis is false. You design an experiment or observation to check. You look. You update your belief based on what you find. The natural void hypothesis makes clear predictions. Void regions should show specific temperature signatures in the cosmic microwave background, specific galaxy distribution patterns at their boundaries, specific internal velocity fields consistent with gravitational drainage. Those predictions have been tested. They broadly hold. The technological void hypothesis also makes a prediction. Void regions should contain no detectable light from enclosed galaxies. That prediction is also confirmed by the data. Both hypotheses predict darkness, and darkness is what we observe. The test that would distinguish them, some observation that the natural hypothesis predicts, but the technological hypothesis does not, or vice versa, has not yet been designed in a form that current instruments can execute. The waste heat argument comes closest. A civilization enclosing galaxies must still radiate energy, as infrared emission from its enclosing structures. Thermodynamics is non-negotiable on this point. An anomalous infrared background in a void region, above what residual natural sources could produce, would be a potential fingerprint. Several researchers have proposed exactly this search. It is technically feasible. The sensitivity required is challenging, but not obviously beyond reach for next-generation instruments. If such a signal were found in the Bhuta's void, or in any of the other extreme supervoids in our catalogue, it would be the most significant observation in the history of science. If it is not found, it narrows the parameter space but does not close it. A sufficiently efficient civilization might radiate at temperatures or wavelengths we have not yet searched with sufficient sensitivity. We are left, then, in a position that science rarely occupies and is not entirely comfortable with. We have a hypothesis that is logically coherent, physically consistent, and observationally indistinguishable from the null explanation. We cannot confirm it. We cannot currently falsify it. We can only acknowledge that the data we have is consistent with it, and that the test required to rule it out has not yet been performed. 8,000 voids, each one dark, each one mapped and catalogued and classified as empty by instruments that can only detect what emits light. Each one, in the strictest sense, an open question. The darkness is confirmed, the emptiness is assumed, and the distance between those two statements is where the most interesting science of the next century may eventually happen. Part 20. The Final Thought Experiment. Let us run one final thought experiment, not because it resolves anything, but because it is the most honest way to describe exactly where the evidence leaves us, and honesty, in a discussion this large, feels like the least we owe the subject. Imagine two possible universes, not two universes with different physical laws, or different constants, or different histories at the quantum level. Two universes that are, in every measurable respect, identical. Same age, same large-scale structure, same distribution of filaments and clusters and walls, same catalogue of voids. Both contain a large, anomalous supervoid in the direction of Bhuta's, with roughly 60 detectable galaxies inside a region that should, by every reasonable cosmological estimate, contain somewhere between 2,000 and 3,000. Both contain a KBC-scale void 2 billion light-years across, with our galaxy sitting near its centre. Both show a cold spot in the cosmic microwave background in the direction of Eridanus, imprinted in the oldest light in the universe, still not fully explained by the supervoid sitting in front of it. Both show the same Hubble tension, that persistent, stubborn disagreement between the expansion rate measured locally and the expansion rate inferred from the early universe, unresolved after more than a decade of increasingly precise measurement. In Universe 1, all of this is natural. Every void, every anomaly, every unexplained tension in the data is the product of standard physical processes operating across 14 billion years. The quantum fluctuations seeded the density variations. Inflation stretched them, gravity amplified them, dark energy accelerated their growth. The Buddha's void is an extreme outlier, sitting at the uncomfortable tail of the probability distribution, but still within the range that a universe governed by standard cosmology could plausibly produce. The cold spot is a statistical fluctuation, or a partially explained supervoid effect, or something we will eventually account for with better data. Hubble tension will be resolved by some systematic error we have not yet identified, or by a modest extension of the standard model that does not require anything radical. Everything we see, every anomaly, every gap, every number that does not quite fit, is just physics doing its thing across billions of years of cosmic evolution. The universe is empty because emptiness is what physics produces. The silence is silence because there is nothing making noise. In Universe 2, most of this is still natural. This is important to say clearly, because the alternative scenario is not a proposal that the standard model is wrong, or that physics is broken. Most voids, in Universe 2, are exactly what the standard model says they are. Ancient, enormous, naturally formed regions of organised emptiness, produced by the same quantum fluctuations and gravitational drainage and dark energy expansion that produced them in Universe 1. The physics works. The standard model is broadly correct. The cosmic web is real, and its formation is well understood. But some of the voids are not natural. A few, perhaps several. Perhaps at the extreme end of the hypothesis, many. In some of those voids, something else has happened. Something that a redshift survey cannot capture, because it does not emit light at redshift detectable wavelengths. Something that a galaxy count cannot reveal, because it has already consumed or enclosed the galaxies that would otherwise be counted. Something that has been operating quietly and efficiently for long enough that the region it occupies has crossed the threshold from dim to dark to indistinguishable from empty. Whatever was there, whatever is there, has gone quiet. Not gone. Quiet. Still present. Still operating. Still drawing energy from enclosed stars and directing it toward purposes we cannot imagine from our position on the edge of a filament in a young civilization with instruments designed to find things that glow. Now here is the part that should settle into you slowly rather than hitting all at once. The sky we observe from Earth is identical in both universes. Completely, perfectly, instrument verifiably identical. The surveys we run, the galaxy counts we compile, the void catalogues we publish, all of them return the same numbers in both universes, because the numbers come from detected light, and in both universes the voids are dark. The papers published about void statistics, void dynamics, the Bootus anomaly, the cold spot, Hubble tension, every paper, every dataset, every conclusion would be word for word the same in both universes, because they are based on identical observational data. We cannot, from our current vantage point, with our current instruments, operating on our current assumptions about what we're looking for, determine which of these two universes we actually live in. This has a name in the philosophy of science. It is called epistemic indistinguishability, and it is importantly different from ordinary ignorance. Ordinary ignorance is a gap. It is the space between what we know and what we could know if we looked harder, built better instruments, ran more sensitive surveys, waited for technology to catch up with the question. Ordinary ignorance is uncomfortable but manageable. Science is very good at closing gaps. It has been closing them for 400 years with remarkable consistency. Give it time and better tools, and ordinary ignorance tends to resolve. Epistemic indistinguishability is something harder. It is not a gap that better instruments will definitely close. It is a boundary, a place where the limits of what we can observe intersect with the limits of what, under certain hypotheses, can be observed at all. The void is too dark for our current instruments to see into clearly, and the thing that would make it not empty, if anything does, has, by the logic of the hypothesis itself, already arranged its affairs so as to be undetectable from the outside. It has removed itself from our view not by moving away but by going dark. And a search for something that has specifically optimized itself to be undetectable is a search with a fundamental structural problem that no amount of sensitivity improvement fully resolves. There is something philosophically specific about this that is more unsettling than straightforward ignorance, and it is worth being precise about what it is. We are accustomed, in science, to knowing what we do not know. We know we have not measured the interior of a neutron star directly. We know we have not detected a graviton. We know we do not have a complete theory of quantum gravity. These are known unknowns, gaps with clear edges, problems with defined shapes, questions that we expect future work to answer. We are uncomfortable with them, but we understand their structure. They fit into the normal framework of scientific progress. This is different. This is a situation where what we do not know may be, in principle, unreachable by any instrument operating on the physics we currently understand, aimed in the directions we currently look, designed around the assumptions we currently make about what a detectable signal looks like. The voids may not just be regions we have not yet examined carefully enough. They may be windows into a stratum of the universe's reality that sits, by design or by the logic of extreme technological development, permanently outside the reach of any observer at our level. Not hidden in the conspiratorial sense, just operating at a remove from the electromagnetic spectrum in ways that our entire observational infrastructure was never built to address. And so here is where the evidence actually leaves us, stated without dramatization and without false comfort. The universe is not full. The dominant structural feature of everything we can observe is absence, organized, ancient, evolving absence that fills somewhere between 60 and 80% of cosmic volume and shapes the behavior of the matter that exists at its edges. We live in that absence. Our galaxy sits near the center of a 2 billion light-year supervoid, and the effects of that position may be quietly distorting our most fundamental measurements of how the universe expands and how old it is and what its ultimate fate will be. Voids are not accidents. They are the inevitable products of quantum mechanics, inflation, gravity, and dark energy operating across cosmic timescales. They have histories, they have internal geometry, they interact with light passing through them in measurable ways. They grow, merge, and evolve in ways our models capture reasonably well, but not always completely, and not always comfortably. Some of them remain genuinely unexplained at the level of detail we can currently resolve. Bhutas, still sitting there after more than 40 years of observation, still too empty for comfort, still internally structured in ways that raise questions the standard model answers only partially. The cold spot, still anomalous, still not fully accounted for. Hubble tension, still unresolved, still whispering something about our position, inside an emptiness we have not fully learned to read. And underneath all of it, the possibility we cannot dismiss and cannot confirm, the emptiness might not be empty. Not because we have evidence of occupation, but because we have no means to confirm genuine vacancy. The same physics that explains how natural voids form also tells us, with complete logical consistency, that a sufficiently advanced technological process would produce something that looks, in every way our instruments can currently measure, exactly the same. We see only what emits light. We map only what we can detect. We call empty what returns no signal. But the absence of a signal is not the same as the absence of something to signal from. The greatest uncertainty in cosmology may not be dark energy, or quantum gravity, or the internal structure of the most extreme supervoids in our catalogue. It may be simpler and more profound than any of those. We do not know what we are not seeing. We do not know, and we may never know, with the tools we currently have, whether the darkness between the filaments is genuinely empty or merely patiently, deliberately quiet. The universe's greatest mystery may not be what exists in space. It may be what the emptiness has learned to do with the light